CodiLime on the stage.
Hello. My name's Milczek. I'm here with Michał Tadeusiak, and we're going to describe the winning solution of the AAIA'16 Data Mining Challenge, which was about predicting dangerous seismic events in coal mines. And even though it's not deep learning and neural networks, we hope that there are valuable insights and that we can show. So to start, we got a lot of data from multiple coal mines located in Poland, and they have sensors that detect seismic events, and they wanted to know if in the next 8 hours after the measurements, dangerous seismic events takes place. So basically the total seismic energy exceeds a warning level, where they have to get people and equipment out of the coal mine. And even though the data is naturally a time series, the organizers had to make decisions as to enable the competition to take place and be tested, because we do have total seismic energy measurements. So if we had the whole time series for the training and the test data, we would only have 24. Last 8 hours would be the only part where it would be interesting. The rest could be just derived from the data. So they made some decisions, and I'm gonna talk about it in a second. So the training set was quite large because we had over 100,000 observations, and the test set was small, and that was to prevent people from just taking the total seismic energy and finding out the exact time series. So we had some easy features, like the ID of the working site. There were multiple coal mines and working sites in the coal mines, and we had statistics like the overall energies. We also, and that's important, we had expert hazard assessments, and so we actually had a baseline to start. We could just start by getting experts' opinions, and it would already be a good model. So we had to improve on that, and we had 22 time series, which were all 24 hours long. And even though they were time series, we decided not to use convolutional neural networks, because 24 is not really a big number, and we thought they weren't needed. And they weren't needed to win, it turns out, but there were also teams who used convolutional networks, and they had good results too. One important thing is that we also got features that were specific to coal mines and specific working sites, and most of those features gave us information like the height of the marine working site, or even names of the regions. And you have to always be very, very careful with such features, because certain model types can make it, it's easy for certain model types to just to just find patterns that will find out the exact coal mine where the data comes from. And if that happens, you cannot assess the. It's harder for the model to generalize to new working sites. So you have to determine if such features are even needed. Okay, is everyone familiar with the AUC metric? Okay, so that's not something I need to describe, fortunately. And the first thing we did was look at the data and the different coal mines or working sites. And there's already some decisions to be made here. For example, we noticed that there are coal mines in the test set that are not present in the training set, but there are also coal mines that are in both sets, and some that are only in the training set. And the decision we had to make here was if we want to build two separate models. Why would we build two separate models? Because we need different methods for the model to be able to generalize to new working sites, and we need different models for the same working sites. I mean, we can, let's say, overfit a bit more when we generate results for the same working sites that we had in the training set, and it's not really overfitting, it's just fitting. But as soon as we try to predict for new working sites, it probably is overfitting. Oh, and one more thing. Some of the working sites had 0% warning frequency, and there could be two reasons for that. One reason is that there are actually no dangerous events in a coal mine, or perhaps some of the sensors do not work. And as you can see, there is a coal mine where warning frequency is 0, but the total seismic energy is actually greater than 0, so we know there is some data coming from there. And we have two working sites where the total seismic energy is 0, and that sounds unreasonable. That probably shouldn't happen, and we had to make a decision if we want to leave those or completely drop them from the training set. And such decisions should not be made by just looking and deciding, because perhaps we can construct a validation procedure or evaluation procedure which is trustworthy enough to answer that question for us. And basically that's one of the things that we want everyone to take out of this presentation. If you don't have to make a decision, if you can just evaluate both options, then you probably should, every time. Okay, I just said all that, I'm sorry. And for the evaluation, we actually used 3 different validation procedures, because the more validation procedures, the better. And actually in competitions, and sometimes in real life cases, but in competitions it's much easier, you can actually choose a validation method and validate the validation method. For example, you just take models, you see how they perform on different validations, and see which of the validation best correlates with the public scores that you get from the organizers. Of course, you have to take those with a grain of salt, not to overfit to the actual public leaderboard scores. But if you keep that in mind, you can do that. And we used 3 different procedures. One of them was leave one location out, and that would be the procedure best suited to check the model's performance on new working sites, because we would just take one working site out of the training set and construct a model, check the model, and repeat that. It's actually a variation of cross-validation, but it divides into subsets by the working sites. And we also had a normal k-fold cross-validation that's random. And that's probably and usually the first thing that everyone does, or perhaps just sampling a test set. And the models That method, just simple k-fold cross-validation, was promoting overfit models quite a lot. So we did not use that in the final solution. And the third procedure we did was train test splits, because we decided to get one model, even though we had to predict for both new working sites and old working sites. And we decided to do it on one model, not to have to deal with the problems with AUC metrics, because it's hard to combine predictions from two different models and maximize the AUC. So that was one of the decisions we've made. In real life case, of course, there would be no decision to make. We would just build separate models. But for a competition, we had to make that choice. And the train test split was a validation that wanted to take into account both old and new coal mines. So there were we would take some new coal mines into the test set or the evaluation set, and for most coal mines we would cut a consecutive fragment of the data so that the model cannot pinpoint the exact time of the measurements. Because for just k-fold random cross-validation, it could. And I want Michał to describe the solution, because he's the author of the best solution, and I just wanted to talk about something.
Okay, hello everyone. So I'll talk more about actually not only feature engineering, but also how we trained the model, how we found the best meta parameters, and what results we got. So Janek already mentioned about the data. The data was quite large set of values, and majority of them were a time series of seismic activities. And the problem was that most of the time nothing interesting, dangerous happening. 66% of the training set was just zeros. So the first thing was to basically dense it, make a more dense representation of the data set. And we went for a lot of different kinds of aggregations. So we kept all the already aggregated features as total seismic energies or sums of them. We kept also the experts' assessments as they were. However, we added extra one, which was just an average over the four different types of assessments. We sum over entire time series of numbers of events within certain energy levels, and some of them we added some averages, basically lots of these kind of aggregations. However, what we've done more is to make some, let's say, handcrafted aggregations based on the importance of relative importance of numbers we had in this time series. So you can imagine, and I think it's quite easy to, let's say, predict that the closer we are to the prediction period, the more important the time series got. So we trained several XGBoost models based on this time series, and we are measuring so-called feature importance, which is F-score in XGB, and it's simply number of times the feature was used within the splits. And as here you can see that if we speak about some average energies of the most active geophones, this is the short name for this, the 5 last ones are relatively more important than the previous ones. So based on this kind of information, we made this kind of analysis for all these time series. We made averages based on only last values. We are doing some weighting averages where we were weighting more the last ones. We are also using some different measures, standard deviations, mean maxes, and we are also using absolute values. A lot of these kind of things. In the end, we had 133 features from 500 something, 40 something. So it was 4 times less and much more dense information. And what's important here, it's not only that it's dense information, it's also that we kind of, by aggregating, we make our models less vulnerable to some weird fluctuations that may appear in the data. We also had this additional information that Janek mentioned already, which was metadata, out of which we used actually only main working height. So it was, let's say, the height that the works were having. And then the thing is, we didn't, as we were building a model that was supposed to be generalizing well. We didn't want this feature to anyhow leak any information about the main working site. And as you can see from this figure, so here are working sites, and here are the on the left side, these small lines, they show the height of the working site. So for some of them, like for this one, like this is a single number which identifies perfectly the working sites. You can see it here. So we wanted to preserve this information, but in the same time, not to make a proxy for a working site. So we randomized this data. We add some Gaussian noise, and now you can see that. So we preserve the information, not maybe like 100% of information, but we prevented our model to be able to infer the working site from this data. Okay, but apart from so it was 133 features, but we decided also to make interactions. And in this case, they were just Payrus products, and it was a lot of them. We produced over 6,000 different interactions, and it's an overwhelming number. So we wanted to assess which of them are important, can add some more value. Again, we use this feature of XGBoost models that we like very much, which is assessing feature importance. And we trained many different models based on these interactions, and selected close to 1,000 of them, which seem to be the most relevant. And we used them. We tried with different models. These were tree-based models, like gradient boosted trees, XGBoost, extra trees classifier, but also some other models like logistic regression, neural networks. In the end, the tree-based models were the best in this case. As I mentioned, we had quite a lot of features, and we decided to do kind of randomized feature selection. So we were running thousands in case of XGBoost, which is quite fast, and hundreds of extra tree classifier models. Each of them was trained on different data, on different features. So for each of them, we are drawing from 20 to 40 regular features and 10 interactions, and we produced a lot of them. And in the end, we built an ensemble of models. The main models within this ensemble were extra trees and XGBoost based on all the regular features, and then 20 best interactions, and also 20 of extra trees and 20 of XGBoost based on the best subsets. And the final submission scored close to 0.92 within this AAIA measure, which turned out to be 0.94 almost in the private leaderboard, and it was the best in the competition. Maybe this measure, it's not telling too much, so we decided also to show you what kind of accuracies we can expect from these kind of models and with this data. So precision was 30%, which doesn't seem to be a lot, but actually, no, it's always very worthy information if we talk about safety of within coal mines. And I think the most important thing is that this data was actually, it was real data collected in Polish coal mines where the infrastructure is already installed. And these models can be just taken, retrained with new data, and they could serve to within the coal mines. We're hoping it will happen. We're talking about it during the conference when we presented the results. If you want to read more about it, get to know more, visit our blog, DeepSense.io, which is a brand of CodiLime for data analysis. You can read more. So thank you very much for attention, and if you have any questions, we're happy to answer.
So questions? Anyone? Okay, one question.
Probably I could have asked you guys during the lunch or something, but how did you blend it exactly? What did you use for blending the models?
Okay, so in this very case, as the measure was out, basically the funny thing here is that the distributions we had, maybe I will show an example. I have some extra slides, in case of questions. How the distributions, no, I have some of them. These were the interactions, if you were asking. These were some, how the data look within, with respect to total seismic energies, and these are these gaps when nothing was happening in that strange. Okay, but coming back to the topic. Okay, so different distributions from different models. This is from XGBoost, and you can see that it's so it has two modes. One, just very low scores corresponding to no warnings, and some some more, some not zero scores corresponding to close to warning areas, but extra trees were giving different distributions, and it's very hard, to make these. That's what also Janek said. That's the reason we decided for a single model, because it's just if you have different distributions, it's hard to couple them together. In this case, because of Auc, we could just average the ranks. So we sorted all of them, and then basically we have ranks from one model, from the other model, and then we average the ranks, and that was our blending strategy.
Okay, one more.
Okay, guys. You're winning some competitions from time to time. I'd like to ask you, what is your strategy in terms of choosing the tools? Because I've seen that you've used scikit-learn, XGBoost, which I would go for too. I think that it always wins in Kaggle competitions. Are there any other tools that you're using?
Okay, so very basically my first recommendation, as I always say, is to just create reliable validation procedures and just test which tools to use. That's my first answer. And my other answer is that actually sklearn has a pretty good base of algorithms, so anything not deep learning or in other ways neural network related, sklearn suffices pretty much every time.
Plus XGBoost.
Plus XGBoost, of course, because for some reason gradient boosting trees from sklearn are slower and worse. But I never checked why. I just knew that it's true.
So when building predictive models on time series that end up with a classification layer, it's always a problem how to do the transition from the time series to the classification. So could you just say a bit more about how you did it? I didn't quite catch it. If you in the end treated every record independently, or you did it in sliding windows. Could you get a little bit more into that?
Okay, I'm gonna start by saying that we actually tried a lot of different things. We tried sliding windows. We tried increasing windows. So like last hour, 2 last hours, 4 last hours, 8 last hours, things like that. And Michał actually went on and automated the process. So I'm gonna let him talk about that.
Okay. Did I? So in this case, there was no sliding window, let's say. No, I mean not like implicitly. I was just aggregating again data within different windows, focusing more on the data which was closer to the detection period. So because the training data was consecutive, so you would have each next row within the data was just shifted by an hour, then you could kind of say I was using sliding window. But in the end, every row, aggregations from every row was just a single observation. So. Yeah.
Okay. Thank you guys one more time.
Thank you.
Our next speaker.
By the way, can I just say one thing? Because when I said that we use sliding windows, I mean we as a team, not we as Michał, because Michał did something else. So in case you thought